Have you ever wondered if the Earth might actually be shaped like a pancake? Let's unpack the intriguing concept of our planet's form. Through the ages, the Earth has been envisioned in various ways. Ancient Greeks like Aristotle observed lunar eclipses and deduced the Earth's roundness from the shadow it cast on the moon. Meanwhile, other civilizations pictured the Earth as flat, a vast plain surrounded by unknown waters. The truth, however, is more complex than a simple choice between round and flat. While it's widely accepted today that Earth is round, describing it as a perfect sphere is a bit of a stretch. This celestial body is actually an oblate spheroid, a sphere that's slightly squashed at its poles and bulging at the equator, thanks to its rotation. This subtle but significant deviation from a perfect sphere has fascinating implications for everything from geography to physics. So what evidence do we have that the Earth is round but not perfectly spherical? Let's dive in. Astronauts see it, satellites capture it, but what exactly are they showing us? Ever since Yuri Gagarin orbited the Earth in 1961, humanity has had a literal bird's-eye view of our planet. From these unique vantage points, astronauts and machines alike have snapped countless photographs, each one reinforcing the image of Earth as a glowing orb suspended in the starry void. As the space age progressed, so too did our technology. Satellites equipped with cutting-edge cameras now orbit Earth, sending back images that are not only breathtaking, but also scientifically invaluable. These photos consistently show a round Earth, with the curvature clearly visible even from low Earth orbit. But here's where it gets a bit technical. The lenses used in space photography, like fisheye lenses, can distort images, making the curvature of Earth appear more pronounced. This optical effect can lead to misunderstandings about the shape of our planet. It's crucial to note, however, that even with this distortion, no amount of lens manipulation can fabricate a round planet from a flat one. The consistency of these observations across different satellites under various conditions and with multiple types of equipment underscores a fundamental truth. But as compelling as these images are, they represent just one piece of the puzzle in understanding the true shape of our planet. Yet these images alone aren't the whole story. Let's look deeper into the science. Why do ships seem to disappear hull first as they sail away? This phenomenon has fascinated observers for centuries, and is a cornerstone piece of evidence for the curvature of the Earth. Imagine standing on a beach, watching a ship sail into the distance. Gradually, the hull, or the base of the ship, vanishes from sight, followed by the midsection, and finally the top of the ship, perhaps the mast, is the last to be seen. Why does this happen? It all boils down to the Earth's curvature. Here's a simple way to visualize it. Think of the Earth as a vast sphere. As the ship moves away, it begins to descend below the horizon, which is the line where the sky seems to meet the sea. This horizon exists because of Earth's curvature. The parts of the ship that disappear first are those closer to the waterline. Since they're further from your eye level, they dip below the horizon before the higher parts of the ship. This everyday observation hints at a round Earth, but there's more to consider. Why does gravity pull us down towards the Earth's center? It's a question that might seem simple, but reveals the profound nature of our planet. Gravity, that invisible force that holds our universe together, operates under the law of universal gravitation. This law states that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Now consider the Earth. If our planet were, say, a perfect cube or a flat disk, the gravitational pull would not be uniform. Objects on the edges or at different elevations would experience gravity differently. Some might be pulled slightly sideways, others not as strongly downwards. This would result in a chaotic environment where water might not find its level, and buildings might need to be constructed differently to withstand different gravitational pulls at different points. However, the Earth is not a cube or disk. It's an oblate spheroid, slightly flattened at the poles and bulging at the equator, yet remarkably close to a sphere. This shape allows gravity to pull everything directly towards the center of the mass from any point on the surface. Whether you're skiing in the Alps or surfing in Hawaii, gravity pulls you straight down, not askew. This consistency in how gravity acts all over the planet is what keeps our feet firmly on the ground and our world in balance. The consistency of gravity's pull supports a round Earth, aligning with our next point. How have explorers traveled around the world if it's not round? Imagine the daring voyages of Ferdinand Magellan in the 16th century, whose expedition marked one of the first circumnavigations of the Earth. This monumental journey was only possible because our planet is a sphere. If Earth were flat, Magellan's ships would have reached an edge, an end, but they didn't. They continued, navigating the vast oceans, eventually returning to their starting point, thus making a complete loop. Modern aviation further illustrates this point. Flights routinely travel in arcs that are shortest on a spherical surface known as Great Circle routes. For instance, a flight from New York to Tokyo often passes over the Arctic, reducing the distance and flight time. This would be inexplicable on a flat Earth model. Now let's talk about time zones. They're based on the Earth's rotation, with the planet divided into 24 vertical sections. Each zone represents 1 hour difference from the next, correlating with the Earth's rotation speed of approximately 1,000 miles per hour. This system ensures that noon is roughly when the sun is highest in the sky, regardless of your location. Imagine a world without time zones. Noon would be the same moment in New York as it is in Tokyo, creating chaos in our daily lives and global interactions. Only a spherical Earth, rotating on its axis, allows for such an orderly progression of time across the globe. These global journeys and our daily timekeeping further confirm the Earth's roundness. Ever noticed how the Earth casts a round shadow on the moon during a lunar eclipse? This curious phenomenon has fascinated observers for centuries. Let's delve into the captivating world of solar and lunar eclipses and how they offer clues about the shape of our planet. During a lunar eclipse, the Earth comes between the sun and the moon, casting a shadow on the moon. This shadow is always round, a key observation that stumped ancient astronomers. If the Earth were flat, one would expect the shadow to be elongated or irregular depending on the angle of the sun. But it's consistently round, regardless of the time of year or the angle of the eclipse. Similarly, during a solar eclipse, when the moon passes between the Earth and the sun, it casts a shadow on the Earth. Observers in the path of this shadow experience a temporary darkness known as totality. The very mechanics of a solar eclipse are dependent on the spherical shapes of the sun, moon, and Earth, aligning perfectly to create this stunning event. Historically, eclipses have been pivotal in shaping our understanding of our world. Ancient Greeks, such as Aristarchus and Eratosthenes, used observations of solar eclipses to estimate the size and distance of the moon and sun, further supporting the spherical nature of celestial bodies. In modern times, eclipses continue to be a powerful tool for scientific study, allowing astronomers to observe and measure celestial phenomena otherwise hidden. The round shadow during eclipses is compelling evidence that our home is a sphere. Why do these revelations about Earth's shape matter in our everyday lives? Well, let's start with the basics. Scientific literacy. Understanding the true shape of the Earth isn't just academic knowledge, it's foundational to how we perceive and interact with the world. When we grasp scientific facts, we're equipped to make informed decisions, from voting on environmental policies to understanding climate change. Now consider technological advancements. GPS systems, for example, are an integral part of our daily lives, guiding everything from your personal road trips to logistics and global trade. The accuracy of these systems hinges on a precise understanding of the Earth's shape. A misconception could lead to errors in navigation and discrepancies in data that could affect millions. Moreover, global communication systems, including satellites that orbit the Earth, rely on our understanding of its geometry. These satellites enable everything from international phone calls to broadcasting live events globally. Imagine a world where satellite placements were based on incorrect assumptions about the Earth's shape. The results? Poor communication, disrupted broadcasts, and even compromised national security. In essence, the shape of the Earth impacts various aspects of modern infrastructure and plays a pivotal role in the interconnected global economy. Our understanding of this shape is not just about knowing, it's about functioning efficiently in a globalized world. Embracing science and its findings not only enriches our understanding, but empowers our actions. Today we've navigated through space photos, gravity, and eclipses to understand Earth's true shape. As we've seen, the curvature of Earth is evident from images taken from space, where it casts a round shadow during eclipses and curves gently at the horizon. This spherical shape is crucial for the phenomenon of gravity, which acts uniformly, pulling everything toward the center of mass, maintaining our stable orbit around the sun and creating a livable environment. Moreover, the ability to travel continuously in one direction and end up where you started, along with the existence of different time zones, further confirms our planet's roundness. These are not just theoretical claims, they are observations backed by centuries of exploration and scientific inquiry. Understanding the shape of our planet is fundamental, not merely for academic knowledge, but for practical navigation and future space exploration. It challenges us to think critically, question our surroundings, and embrace scientific methods in our quest for truth. Stay curious, keep questioning, and remember, science holds the key to unlocking the mysteries of our universe.